Hello everyone. So, today I will be starting two very important concepts in calculus, which are continuity and differentiability of a function. So far we have studied what do we mean by limits of a function at a point, and we will see that the limits play a central role in defining the continuity and differentiability of a function of point, and in subsequent lectures we will see many applications of these concepts. So, let me begin with defining what do we mean by a continuous function at a point. So, I will discuss what do I mean by continuity of a function at a point. So, we will always assume let f be a real valued function defined on a domain D. So, suppose the function is defined on a domain D, which is a subset of R real number, and suppose A belongs to D, that is the function f is defined as f of A is defined. So, we say that f is continuous at A if f of A is equal to the limit of the function f of x as x approaches A. So, recall that for limit f of x going to A to exist, the function f of x must be defined in some interval, some open interval containing A. So, we say that f is continuous at A if f of x is continuous at x equal to A if there are two conditions. First, the limit of f of x as x approaches A exists. So, first of all, the limit of the function as x approaches A should exist, and second, f of A must be equal to the limit of f of x as x approaches A. let me say here that for the limit to exist, we want the function to be defined in some interval containing a, but not necessarily at x equal to a, right. So, for the limit we do not require the function to be defined at x equal to a, but the continuity definition is that the value of the function at a must be equal to the limit. So, for f to be continuous, so for f x to be continuous, at x equal to a, the function must be defined at x equal to a, and f of a must equal the limit of f of x at x approaches a. So, let us see some examples. So, examples. One. So, consider f of x which is equal to 0 for x less than 0 and 1 for x bigger than equal to 0. So, if you draw the graph of this function, this function is 0 for all x negative, and for x greater than equal to 0, f x is equal to 1. So, this is my x y, and this is the graph of y equal to f of x. So, here what we know is that here limit of f of x at x approaches 0, this does not exist. This is because the left hand limit at 0 of f of x, this is equal to 0, which is not equal to 1, which is the right hand limit at 0. So, since the limit does not exist, so f of x is not continuous at x equal to 0, even though f of x is defined at x equal to 0. We have f of 0 is equal to 1. But if you take any point other than 0, but if a is not equal to 0, then the limit of f of x as x approaches a, this is equal to 1 if a is strictly positive, and this is equal to 0 if a is strictly negative, right. This you can see from this graph, that if we take any a to be positive, then the function is constant 1 in an interval containing this point a, and therefore, the left hand limit and right hand limit are both equal to 1, but if your a is somewhere here negative, then in this interval the function is identically 0, therefore, the limit is 0. Also, f of a is equal to 1 if a is positive and 0 if a is negative. So, therefore, the function f of x is continuous at all points except x equal to 0. Right. Also, if f x is not continuous at x equal to a, we will say that f of x is discontinuous at x equal to a. So, intuitively what does continuity mean? Intuitive meaning of continuity. So, if we can draw the graph of the function, and suppose we have this point a. So, this is the point a comma f of a. So, if we can draw the graph of the function y equal to f of x, then the continuity of f of x at x equal to a means that the graph is not broken near the point a comma f of a on the graph. So, which means that you can draw the graph of this function near this point a comma f of a without having to lift your pen. So, but we will see that this intuitive definition is not enough to make rigorous sense of continuity. So, for example, so for the previous example, f x equal to 1 for x greater than 0 and 0 for x less than 0, or we said for greater than equal to 0 it is 1. If you draw the graph near this point 0 comma 1, you see for x greater than 0 this is 1, but for x less than 0 it is 0. So, you cannot have this not broken for this function. So, here you see that the graph f x has broken graph near 0 comma 1. So, this example, so the previous example was where the function was not continuous or discontinuous at a point because the limit did not exist at that point. But the next example, let us consider the function f of x which is equal to 1 if x is not equal to 0 and 0 at x equal to 0. So, this function it is 1 at all point except 0. So, we draw an open circle here and this is the value 1 and at x equal to 0 this is 0. So, this is the graph of the function f of x. So, in this case again by using the intuitive meaning you can see that this graph is broken at the point this point 0 comma 1. So, the function is not continuous at x equal to 0. In this case if you see here limit of f of x as x approaches 0 this exists and is equal to 1, but the value of the function at 0 this is given to be equal to 0 which is not equal to the limit of f of x as x approaches 0. Hence, the function f of x is discontinuous at x equal to 0. So, we have seen two examples. In one the limit of the function did not exist at a point and therefore, the function cannot be continuous at that point. Another example was where the limit exists, the function is defined at that point, but the value of the function is not equal to the limit. So, therefore, again the function is discontinuous at that point. Now, let us see, let us consider this example f of x which is equal to x times sine of 1 by x, and because I am writing 1 by x this does not make sense for x equal to 0. So, I defined this to be the value of the function for x not equal to 0 and this is not defined for x equal to 0. So, for x equal to 0 I will define the value of the function to be 0. So, this is the function which is 0 at 0 and for any non-zero x the function is x times sine 1 by x. So, here what can you say is f continuous at x equal to 0. So, in this case if you see, if you try to draw the graph of the function x times sine 1 by x, it is very difficult to draw it near the point 0, because as you go close to 0 this function sin 1 by x, it keeps oscillating. So, here let me say it is difficult to draw the graph. So, it is difficult to see whether the graph is broken or not, but let us try to calculate the limit if we can. So, but can we calculate the limit of x going to 0 f of x can be calculated as follows. I think we have seen this example maybe before also. So, how do I so that the limit exists? So, if you look at f of x, let us look at what is mod f of x. This is equal to mod of x times sine of 1 by x, which is less than equal to mod x times mod sine 1 by x, and since sine of 1 by x, we know that it is always between -1 and 1 for all x not equal to 0. Of course, for x equal to 0, sine 1 by x is not defined, but for any x not equal to 0, we know that sine of y is always between -1 and 1. Therefore, mod sine 1 by x, this is less than equal to 1. Therefore, mod of x sine 1 by x, this is less than equal to mod x, and of course, this is because we are taking the absolute value mod, it is greater than equal to 0. Now, we have seen the sandwich theorem. So, since limit of x going to 0 of x is 0, which is also equal to the limit of the left hand side 0 as x going to 0, by the sandwich theorem, the limit of x sine 1 by x, we write mod x sine 1 by x as x goes to 0, this is equal to 0, and this implies limit of x sine 1 by x is also 0. So, the limit of the function, therefore, we have that f of 0 is defined to be equal to 0, and this is equal to the limit of f of x as x approaches 0. Therefore, by the definition of continuity, so f of x is continuous at x equal to 0. So, this example is important because here drawing the graph of the function and then inferring whether the function is continuous at x equal to 0 or not, that is difficult, but by calculating the limit of the function at 0, we saw that that is equal to the value of the function f of 0, and hence the function is continuous at 0. So, later we will let's see some more examples of some functions where it might not be very easy to deduce whether the function is continuous at a point or not, but let me go ahead and discuss another concept, which is differentiability of a function. So, let f of x be a real valued function which means that the range of the function is a subset of real number. Let f x be a real valued function, then we say that f of x is differentiable at x equal to a if the limit of h going to 0 of f of a plus h minus f of a divided by h, this exists. So, note that for f x to be differentiable, at x equal to a, the function f of x must be defined in an open interval containing x equal to a. This is because, see, we are saying that this limit of f of x plus f of a plus h minus f of a divided by h, this limit should exist. So, first of all you see that here there is f of a. So, we must have that f should be defined at x equal to a. Also we are writing f of a plus h and then taking the limit as h going to 0. So, that means that h can be positive or negative and a small real number. So, the function must be defined in some interval. So, if I have a is here, then in some interval near this the function must be defined, then only we can talk about the differentiability of the function. So, now let me explain what this ratio that I wrote f of a plus h minus f of a by h is. So, if you look at the graph of the function, let me write geometric interpretation. So, let me draw a function and let me take this point to be x equal to a. So, this is f of a. Now, I have this point which is, let me call this point as p, which is whose coordinates are a comma f of a, and let us look at another point which is a plus h. Here I am taking h positive. Then there is another point q here whose coordinates are a plus h, and f of a plus h. So, we have this is f of a plus h. Now, if you look at, if I draw this line segment joining the point P and Q, and I draw a horizontal line here, then this part is h and this vertical part, this is f of a plus h minus f of a. So, this ratio, the ratio f of a plus h minus f of a by h, this is nothing but is the slope of the line joining the points P, which is given by a f of a, and Q, which is the point a plus h f of a plus h. Now, what happens as h approaches 0? So, we have to ask whether this limit of this function, this ratio as h approaches 0 exists or not. So, if you see from this graph, as h approaches 0, this point Q approaches P. As h tends to 0, the point Q tends to P. And what happens to, and the secant, that is the line segment joining these points on the curve, that is the line segment joining P and Q, approaches the tangent line at the point a comma f of a. So, maybe let me draw another diagram. We have this point P here, and there is this tangent line. So, as this Q moves and approaches this point P, the secant line approaches this tangent line, and the slope of the secant line approaches the tangent line. So, limit f of a plus h minus f of a divided by h, this is the slope of the tangent line provided the limit exists. Okay, so if the function is differentiable, so if f of x is differentiable at x equal to a, then we denote by f prime a this limit f of a plus h minus f of a divided by h, right. So, if the function is differentiable, that is this limit exists, then this limit is defined to be f prime a, and f prime a is called the derivative of f of x at x equal to a, right. So, the derivative is the limit of this difference quotient if this limit exists, and if the limit does not exist, then we will say that the function is not differentiable. If the limit of the difference quotient which is f of a plus h minus f of a by h does not exist, then we say that f of x is not differentiable at x equal to a. Now, let us look at some examples. So, examples. So, first one, the simplest function is, let us take f from R to R, where f of x is equal to c, a constant. So, let us look at the constant function f of x equal to c for all x in R. Now, here what is f of, so for any a in R, f of a plus h minus f of a, this is equal to c minus c, which is 0 for all h. Therefore, the limit of f of a plus h minus f of a by h, this is equal to 0, because the numerator is 0. So, therefore, f is differentiable at every a, and f prime of a is equal to 0. So, for the constant function, the derivative is 0 everywhere. Next example, let us look at f x equal to x. Now, let us try to calculate again the limit. So, f prime a, this is equal to limit of h going to 0, f of a plus h minus f of a divided by h, which is equal to limit of h going to 0, f of a plus h is a plus h minus f of a is a divided by h, here a and minus a cancels. So, this is equal to limit h going to 0 of h over h, and for any h non-zero h over h is 1. So, this limit is equal to 1. So, for f x equal to x, the derivative f prime x is equal to 1 for all x in R. Okay. Let us try to calculate one more. Let us look at f x equal to x square. Now, if I look at f of x plus h minus f of x divided by h, if this limit as h approaches 0 exists, that will be the derivative f prime x. So, this is equal to x plus h square minus x square divided by h, and then we write x plus h square as x square plus 2 h times x plus h square minus x square divided by h, then x square and x square cancels. So, this we are writing always for h not equal to 0, and this is equal to h times 2x plus h by h. So, this is equal to 2x plus h. Now, we see that this goes to 2x as h goes to 0. So, therefore, f prime x, which is the limit of h going to 0 of f of x plus h minus f of x over h is equal to 2x. So, let me introduce one more notation. So, this f prime x is also denoted by d by dx of f of x or dy by dx, where y is equal to f of x. So, what we have got so far is, so we can write d by dx of any constant function is 0, d by dx of the function f x equal to x is equal to 1, and we saw that d by dx of x square, this is equal to 2x. So far we have seen these three derivatives. Now, one important property is that, suppose f x and g of x are two functions which are differentiable at x equal to a, then the function f x plus g x is also differentiable at x equal to a, and we can write the derivative d by dx. So, we will write this at x equal to a of f x plus g x this is equal to d by dx of f x at x equal to a plus the derivative of g x at x equal to a, that is, this is same as f prime a plus g prime a. So, let us see the proof. So, let me write u x equal to f x plus g x. Then we want to show that u is differentiable at a. So, if I write u of a plus h minus u of a divided by h, this is equal to f of a plus h plus g of a plus h, so that is u of a plus h. This minus u of a is f of a plus g of a divided by h, and this can be written as sum of f of a plus h minus f of a divided by h plus g of a plus h minus g of a divided by h. So, for any h non-zero we have this, and what we know is that the limit of the right hand side, both the limits exist. So, therefore, limit of u of a plus h minus u of a by h as h goes to 0, this is equal to limit of h going to 0 of f of a plus h minus f of a by h plus limit of g of a plus h minus g of a divided by h. This is by the sum rule of limits. Right. We have seen for limits that if the limit of f x and g x exist at some point, then the limit of the sum also exists, and limit of the sum is sum of the limit. So, that is what we are using, and this is same thing as saying that u prime a exists and is equal to f prime a plus g prime a. Another important property is that if I write u of x equal to some constant times f of x for some constant c in real number, and f prime a exists, that is f is differentiable at a, then u prime a exists and u prime of a is equal to c times f prime a. So, to prove this, again we write what is u of a plus h minus u of a by h. This is equal to c times f of a plus h minus c times f of a divided by h, which is equal to, I can take c common, and then I have f of a plus h minus f of a divided by h, and we know that this limit is equal to, so I will simply write this tends to c times f prime a as h tends to 0. Therefore, u prime a is equal to c times f prime a. So, using these two results, we can say more generally that if u of x is c1 times f x plus c2 times g of x and f prime a g prime a exists, then u prime at a is equal to c1 times f prime a plus c2 times g prime a. This is simply combining the previous two properties. So, we know that u prime of a is equal to, by the sum rule, this is equal to d by dx at x equal to a of c1 f of x plus d by dx of c2 g of x at x equal to a, and by the constant multiple, this is equal to c1 times f prime a plus c2 times g prime a by the previous two results. Okay. So let us use this result to calculate some derivatives. So, example, let f x equal to x square minus 3x plus 2. Calculate f prime at 3 if it exists. So, what we know is that we know the derivative of x square, derivative of x and derivative of constant. So, since d by dx of x square is 2x, d by dx of x is 1 and the derivative of the constant 2 is 0, we have that the derivative of x square minus 3x plus 2 is equal to 2x minus 3 times the derivative of x is 1 and plus 0. So, this is nothing but f prime of x. So, in fact, for any x the derivative exists at x and is given by 2x minus 3, and therefore, f prime at 3 you just have to plug in x equal to 3 is 2 times 3 minus 3, which is equal to 3. Right. So, using this sum rule and constant multiple rule, we can calculate the derivative of a combination of these functions if I know the derivative of each of them. So, we will stop here, and in the next class we will learn some more properties and then calculate derivative of some more functions. Thank you.